Hello everyone, this is the Gothic Chess King. I did post a video showing the solution to a math problem I composed back in 2016, and a couple of you contacted me. One of them had a son that was in college who was having problems with a calculus homework problem. And I decided to do a video on that because it was kind of intriguing. I hadn't had calculus for decades now, and it's amazing how much you forget. um, anyway, so the problem is basically this. You see there's a parabola here in the form of y equals x squared, and inside it you're going to inscribe a circle of radius 1. The question is, what's the shaded area that's below the circle yet above the parabola? And you can see that in gray here. It almost looks like there's not enough information because one of the first things you have to do is set the equation of the circle equal to the equation of the parabola to find the points of intersection, and you want to integrate from one side to the other to be able to get the areas under the curve. So that's kind of a hint at what you need to do to start solving the problem. So as always, I start by saying, what's the strategic knowledge you need before you can begin to solve such a problem? Obviously, the first thing you need to know is the algebraic form for the equation of a circle. You will need how to solve for the common points of intersection on a Cartesian plane. You need to know how to apply the solution to the quadratic equation. And in terms of calculus, obviously you have to know how to do an integral to compute areas under curves. But in this particular case, you're also going to need to know one of the more advanced integration techniques called trigonometric substitutions. And you'll see why as we get to that in a little bit. And not only that, you're going to have to recall some of those fundamental trigonometric identities. Okay. So the first thing to recall from your algebra days is the general form for the equation of a circle. And if they picked the letters H and K because by the time you get to graphing circles in algebra, they used up just about every other reasonable letter close to the beginning of the alphabet. So if the x-coordinate is H and the y-coordinate is K, the general form for the equation of a circle is x minus h, the quantity squared, plus y minus k, the quantity squared, is equal to the radius squared. And in the case of this problem, we know the circle has a radius 1, and it intersects the y-axis, so the value for h is going to be 0. So going from the general form to the specific form, we have equation 2. You're just going to have an x squared term since the h value is going to be 0. When you look at the original circle, you see yh is 0. And the third equation is just the equation of the parabola. Again, I say here, if we knew the location of the center of the circle, we could construct the complete equation of the circle, set the equations equal to one another, and determine what those actual coordinates are. We're not there yet, though. You notice here in equation 3, y equals x squared, and we have an x squared here in equation 2. Well, x squared is just y, so that's going to be our first step. We're just going to do that substitution and then rewrite the equation only in terms of y. So you have y plus the quantity y minus k squared equals 1. And rearranging those terms, after you multiply out the y minus k quantity squared terms, and putting them in the same order as the coefficients for the quadratic equation solution, you have y squared plus, and in front of the y you have the quantity 1 minus 2k, and at the end you got plus k squared minus 1. Now, here's the thing. Usually you say ax squared plus bx plus c equals 0. In this case, I mean, c is just a constant. It doesn't matter that it's an expression here. It's just k squared minus 1. And the coefficient in front of the y, again, it's not one term. It's just 1 minus 2k. There's no reason why we cannot substitute those into the solution for the quadratic equation. So, to derive what y is, we're going to use a equals 1 because the coefficient of y squared is 1. B is 1 minus 2k because we have a 1 minus 2k in front of the y. And as I mentioned earlier, c is k squared minus 1 because that's the expression here. Alright, plugging that in, doing the math and simplifying, thankfully you have a plus 4k squared here and a minus 4k squared. And that leaves you with just 1 plus 4 is 5 minus the 4k here under the radical sign. But once you get to this point, you say, all right, great, what do I got? I have y equals 2k minus 1 plus or minus the square root of 5 minus 4k all over 2. So you got two expressions, both of them involve k. But now you have to do a little bit of analytical geometry and look at the problem again, okay? You see this red line here. That's the actual y coordinate of where the parabola touches the circle, you notice. And there's symmetry across the axis there. So both of the y coordinates are going to be exactly the same. The x coordinates are going to be mirrored and different. So your 2k minus 1 plus square root of 5 minus 2k over 2 is going to be equal to the same expression using the minus instead of the plus sign. Okay. Picture is worth 1,000 words here, and that's what equation 5 is. I took the plus or minus expression for y and set the plus side equal to the minus side. Now you're going to get a lot of simplification here, obviously, right? And some of you got stuck once you get to this point. You say, oh, I got this on both sides, so I get 0 equals 0. No, you don't get 0 equals 0. You want to, you have the square root of 5 minus 4k equals the negative of the square root of 5 minus 4k. So add the square root of 5 minus 4k to both sides, right? You're going to have double that on the left side and 0 on the right side, all right? And then, of course, divide both sides by 2 because you got 0 on the right, nothing happens. And you can square both sides because on the right, nothing happens. And you're just left with 5 minus 4k equals 0. And, of course, k equals 5/4. So after all that, we now know the equation of the circle. That's equation 6 here. X squared plus the quantity y minus 5/4 squared equals 1. Now, again, the next step is making use of the fact that the parabola y equals x squared is going to match the points on the circle where they intersect. So this x squared term in equation 6 is just going to be substituted with the letter y here, calling this equation 7. And when you expand that out, you see it's y plus y squared minus 5y over 2 plus 25 over 16 equals 1. Now, me, I absolutely detest fractions. I don't go through the procedure of trying to figure out what the smallest or least common multiple is to multiply everything by. I just say, what's the biggest number on the bottom, and I multiply everything by it. In this case, that was 16. So you get 16y plus 16y squared minus 40y plus 25 equals 16. And when you simplify that and write it in the order that's amenable to the solution for the quadratic equation, you have 16y squared minus 24y plus 9 equals 0. Okay? Again, easy to precipitate out what the constants are. A is 16, B is minus 24, C is 9. And when you put that in to the solution to the quadratic equation, you start to get some pretty big numbers in there. That minus 24 squared is 576. But beautifully, 4 times 16 times 9 is also 576. So the entire expression under the square root just evaporates. You're left with 24 over 32, which is, of course, 3/4. Again, it's making use of equation 3, y equals x squared. This 3/4 on the y-axis is actually what x squared is. So x is plus or minus the square root of y. So you get plus or minus square root of 3 over 2. And at this point, we could identify what the center of the circle is and both the x and y coordinates for where the parabola touches the circle, and that's shown here. So y is going to be at 3/4, x is going to be minus square root of 3 over 2 on the left and plus square root of 3 over 2 on the right hand side. Okay, now we're not done. You have to rewrite the equation of the circle in the form y equals f of x. Remember, we have it in terms of x squared and y squared, and some additional terms for the circle. So starting back at equation 6, x squared plus y minus 5/4 squared equals 1, what we want to do is put x on the right hand side. So we subtract x squared from both sides of the equal sign, and then we have an expression for y minus 5/4 squared. Well, take the square root of both sides. You have y minus 5/4 is plus or minus square root of 1 minus x squared. So getting y all by itself, you just add 5/4 to both sides. So now you have two equations. Y is 5/4 plus the square root of 1 minus x squared, and y is 5/4 minus the square root of 1 minus x squared. Equation 8 is going to have the bigger values for y. That's the top half of the circle, because you're adding the square root of 1 minus x squared. The equation 9 is going to be the bottom half of the semicircle, because you're subtracting values. So for the purpose of the integration, if you look at the original problem, right, the integration is going to occur on the bottom side of the circle. So you can ignore the equation that corresponds to the top side of the circle. Okay, so now this is what we're looking at. We're going to integrate from negative square root of 3 over 2 to square root of 3 over 2 of the difference of the equations between the bottom half of the circle and the parabola. Remember, when you integrate underneath a curve, you get the entire area of the curve. So in order to just get the shaded area, you need to subtract the area under the circle from the area that's under the parabola, which is why the last term in this equation 10 is minus x squared. So the first part, this 5/4 minus square root of 1 minus x squared, is from the circle, and you want to subtract the area that's underneath the parabola. Otherwise, you get the area that's under the circle. Okay, and this will break apart into 3 separate integrals. Okay. Obviously, the 5/4 dx piece is easy, as is the x squared dx piece, right? When you integrate x squared dx, you just get x cubed over 3. 5/4 dx, the integral is going to be 5/4 x. So plugging in the values. Fortunately, the values on the bounds are symmetrical, so you're basically just doubling the largest number when you actually go through the machinations of creating, precipitating out the number from actually doing the integration. So when you have 5x over 4 bounded on the right hand side by square root of 3 over 2, and the left hand side negative square root of 3 over 2, you're functionally just doubling that number. It's 10 square root of 3 over 2 over 4. Same thing when you have the x cubed over 3 piece that you're going to be working on. Square root of 3 over 2 cubed, square root of 3 over 2 times square root of 3 over 2 times square root of 3 over 2. That's just 3/4 square root of 3 over 2, which is where this number comes from over here. 6 square root of 3 over 8 over 3. We're going to leave this middle integration untouched for the time, and we're just going to simplify this. Obviously, you get 10 square root of 3 over 8 minus 2 square root of 3 over 8, which leaves you with 8 square root of 3 over 8, which is just the square root of 3. So that's where the two integrals on either side of the middle integrand just evaluate to the square root of 3. And from that, you subtract the area under the circle. Okay. At this point, you have to do an integral that has a square root of 1 minus x squared dx as the integrand. And there's no easy way to do this directly, so you use a substitution function that will make your life a lot easier. In this case, and this is standard second level course in calculus, use the trigonometric function here. In this case, x equals sine of theta. Of course, when you take the derivative of the sine function, it's cosine of theta, and don't forget to put the d theta on the end because we're integrating with respect to theta now and not x. And the other thing you have to do is convert the range. We're no longer going from minus square root of 3 over 2 to square root of 3 over 2. That's in the x domain. We are now in the theta domain. And since x equals the sine of theta, that means theta must be the inverse sine of x. So all you have to do is compute the inverse sine of square root of 3 over 2, which of course is pi over 3, or 60 degrees. We'll leave it as radians for now. So our integration range is going to change from minus square root of 3 over 2 to square root of 3 over 2 to minus pi over 3 to pi over 3. And we're going to replace the square root of 1 minus x squared dx with the square root of 1 minus sine squared theta. Don't forget to multiply the cosine theta d theta on the ends. Fortunately, 1 minus the sine squared of theta is the cosine squared of theta. And the square root of cosine squared of theta, of course, is just cosine theta. But we have a cosine theta on the outside of cosine theta again. And that's just cosine squared theta all over again. So at this point, you really want to look up what the integral of cosine squared theta d theta is in an integration table. These are one of those things that they force you to do manually once, and then for the rest of your life they say, turn to the integration table in the back of your book, look it up. And this is the reason why. The integral of cosine squared theta d theta is theta over 2 plus sine of 2 theta over 4. Yeah, like you're going to really want to do that manually every time. No, of course not. So when you plug theta is pi over 3 and minus pi over 3 into that expression here to get the integrand, the value for the integrand, you get pi over 3 plus the square root of 3 over 4. And if you consider that outside here, the square root of 3 is really 4 times the square root of 3 over 4. And this is just 1 times the square root of 3 over 4. 4 minus 1 is 3 times the square root of 3 over 4 minus pi over 3. That's the final answer. It's the square root of 3 times the square root of 3 over 4 minus pi over 3. And for those who are getting dizzy, it's about 1/4. This whole thing is about 0.25. There's the numerical expression down here. So yeah, this was kind of a long problem. It combined both strategic and tactical complexity. A couple of points you get stuck and you don't know where to go next. That's a strategic problem. You don't know how to get to the next step. And tactically, if you don't know how to do the actual calculation, you're going to get stuck. So this had a couple of ways to trip you up. I would consider this a fairly advanced Calculus 2 problem. And there's your solution. And thanks for taking me down memory lane. I haven't had to solve a problem like this since about 1984. Anyway, there's your answer. Good luck with your homework assignment. And I hope to see you guys out there.